An acceleration is speeding up, slowing down, or changing direction. Up to this point in the course, we've only considered accelerations that were changing speed, that is, the magnitude, but not changing the direction. We saw in those situations the object was moving in a straight line. We now want to consider the other extreme. Suppose something is traveling with a constant speed, but changing direction only. We can demonstrate that a situation like that will mean the object is moving along the arc of a circle. In this experiment, you're going to be doing a paper and pencil analysis of this type of acceleration. You will discover by adding vectors together, just as you did in the second lab, that the direction of the acceleration is always pointing towards the center of the circle. For that reason, this type of acceleration is called centripetal acceleration. The materials for this experiment are 2 copies of the large circle, 1 copy of the small circle, a pencil, and a ruler. Consider an object moving along a circular path at a constant rate. The goal is to determine the acceleration of the object at some point in the motion. We have chosen this point for that purpose. We need to identify the center of the circular path and measure the radius. Next, we consider the motion of the object at a time delta t divided by 2 before the point. The velocity vector is tangent to the circle, which is perpendicular to the radius. We then identify the location of the object at a time delta t over 2 after the point. We now subtract the final velocity vector from the initial velocity vector graphically to get the change in velocity delta v, which is proportional to the acceleration vector and pointing in the same direction. Repeat this method of graphical addition for an object moving on the same circle, but twice as fast. But the object will travel twice as far along the arc, so the initial and final locations are twice as far away from the point of interest. For the third case, the length of the velocity vector is the same as the original, but the angle for the starting and ending locations is the same as the second case, because the circumference of the circle is only half the original. Use the graphical results to draw conclusions about the direction of the acceleration vector at any point on the circular path. Also decide on the mathematical relationships between the magnitude of the acceleration and both the speed of the object and the radius of the path. 4 likely possibilities are proportional, inverse proportional, square, or inverse square.